Welcome to the next video in the measure theory and probability course. This is video 14 where we're doing an exercise, and this exercise is Egoroff's theorem. This corresponds to part 1, chapter 1 of the textbook. And so here's the theorem that we're going to prove. It is exercise 1.6. If we have any measurable space with a finite measure mu, then if we further have this sequence of measurable functions f sub n, so they're all going to be measurable and share the same domain E, returning real numbers, and we assume that they converge pointwise on E. Here's what follows from that. Now this, I think it is useful to think of it as almost uniform convergence. So we know what uniform convergence is. By the way, this is sometimes used as notation for uniform convergence, right? So the sequence Fn converges uniformly to F. And sometimes I'll use, right, like there's these two notations. You can also write a U above the arrow, or right, there are different ways of expressing uniform convergence that all mean the same thing. But I think this property, it's helpful to think of it as almost uniform convergence. So if you need to go and refresh yourself from real analysis on what uniform convergence means, please do that. But this is something that I think you'll want to conceive of as almost uniform convergence. And what it means is that if you take any epsilon, and here note that this epsilon is not going to be the epsilon that is used in the definition of uniform convergence, right? So don't think that this epsilon is just like that other epsilon in the statement of uniform convergence. This is a different epsilon. But let's keep going, right? So if you pick any positive epsilon, then there exists a very large measurable set A. So I'm saying here that A is very large. That's just how you want to heuristically kind of imagine what these things are. What do I technically mean by calling it a very large set? What I mean is that the difference between the entire space and this set A is very small, right? You always imagine epsilon is a small quantity. And so here we're imagining that the difference between the entire space and A is very small. So kind of what you're imagining is that A is very big. And then on this set, right, on this very big set that contains almost everything, not everything because it, the difference between it and the entire space can be positive, and so you're missing some points, but on this very large set, you actually have uniform convergence. So that's what I'm calling almost uniform convergence, right? It converges on a very large set, even if it's not converging uniformly on the entire set. And the textbook gives us a hint about how to approach the problem, and in particular, it gives us this sequence of sets indexed by both k and n. So n is going to be the starting index of an intersection, and k is going to kind of control how far apart the functions are throughout the entire space, how far apart they are from each other. So, in effect, for a fixed k and n, we're just talking about one of these sets, and it is the set of all points that stay close together, right? Stay within 1 over k of each other throughout all of E. So that's what E sub k n is, right? Of course, with n controlling the intersection. And I guess we should, think about what's going on there. So with n becoming larger and larger, the intersection starts farther and farther out, right? Because that index j shows up again here in this term. And so if, effectively what that means is that we're like forgetting early functions, right? So by setting n very large, the first several functions don't matter, right? They're not going to feature in any of these sets. So how are we going to approach this problem? Well, having talked about how the index n here seems to control how we forget early functions or in a sense terms in the sequence of sets, that should perhaps ring a bell about lim_sup and lim_inf. So if we recall that, then when you're working with those things, you either take the union of an intersection or the intersection of a union. So here, we perhaps want to think about taking the union of these things and measuring them, of course. Certainly, it is true that this is a monotonically increasing sequence of sets, and you should prove that to yourself if you need to. Also, and it'll be important, right, it's a good exercise to demonstrate that this sequence of sets is measurable. Now, how are you going to demonstrate that each one of these sets is a measurable set? Well, I think it should be somewhat clear that it's some kind of a pre-image of the absolute fj minus f, right, treated as a function. It's the pre-image of this function on a particular interval. And so what you want to do is show that that thing is a measurable function, right? Pre-image of a measurable function is a measurable set. So you want to show that this thing, this absolute fj minus f, is a measurable function. And given what we've talked about already, of course, the difference is measurable. So then you just want to make sure that you understand that taking the absolute value of a measurable function is also a measurable function. But I'll leave that argument to the viewer. So anyway, so we have, right, from that quick argument, that each set in the intersection is a measurable set, and therefore we have confirmed all the conditions needed to apply continuity of measure. So, right, we have this monotone, because we're taking the union, right, after all, right? So again, recalling the definition of E, and the plan is to take the union as n increases. And so we get this monotone increasing sequence of sets. We are unioning them and measuring the union, so we get that that is the same thing by continuity of measure as the limit of each individual measure. Oh, and of course, also this is all justified because the measure mu is a finite measure, meaning the measure of the entire space is a finite number. That then means that any set must have finite measure, right, by monotonicity. So anyway, right, that's just quickly and verbally confirming another thing. Again, to be very careful and so on, I encourage you to write down and formalize the things that I am just talking through very briefly, but it should be relatively doable. Now, while we're on the topic of this union over these sets, let's remark on the fact that if we do union over all choices of n, then this must in fact be the same thing as the entire space. And that is because we assumed earlier that the sequence of functions converges pointwise to f. And so if you pick any particular x, right, fix an x, let's justify this, fix x. I claim that eventually if you set n large enough, then eventually x will be in one of these sets E sub k comma n. Again, keep in mind k is a fixed number, so when we think about how k is used in these sets, then we essentially have a separation between f and the functions in the sequence. And so since the convergence is pointwise, then if you let the sequence of functions go on long enough, then eventually, right, because of pointwise convergence, eventually the separation between the sequence of function values and the function f must eventually go to 0, basically, and in particular, it must eventually be less, that right, this separation must be less than 1 over k. meaning that X is in that set, and it will be in every set after that, right, because it's a monotone sequence of sets. And so anyway, so for this fixed X, because of the pointwise convergence, then therefore X is in E sub k n eventually. I guess I'll just kind of summarize it that way. But and then once it's in one of these sets, it's in every one of them after that, again, owing to how pointwise convergence works. So anyway, the point here is that this union that we are now talking about, the union over all of the EKN for, right, unioning over N, and again, having K fixed, you get the entire space E. So effectively, putting all of this together, we have shown that the limit of the individual measures is eventually just equal to the measure of the entire space. Now from here, we notice that this is where epsilon can become relevant in getting us that very large set. And right, and after all, once epsilon is fixed, which happened a long time ago, we are then in search of this very large set A, and the question is, what is that very large set A? Well, at least we can make a move. I don't think I claim that this is the set A, but at least it gets us close to it, right? That there must exist an index n. There is some index n, right? Because of the limit up above, right? There must exist this index n such that the difference between the entire space and this particular EKN is smaller than epsilon, right? So, so we have the existence of such an index n, and that gets us a particular set. Now, that doesn't look exactly like what we want, but it gets a lot closer if we then apply excision, because all of the measures involved are finite. So by excision, the difference between E and EKN is equal to this difference, which we just said is less than epsilon. So we're getting closer, right? This looks like progress. But what we haven't yet done is get true uniform convergence, because up above that, you know, the fact that, you know, like what's going on that set EKN? Well, it's that the functions all stay within 1 over k eventually on that EKN. And so, so that's not quite what we want, because we don't want them to just stay within 1 over k. We want the separation to become arbitrarily small in the limit, right? We want that uniform convergence, so there should not be this fixed parameter k. So let's summarize what we've just done and see if we can't do something to kind of, in some sense, let k go to infinity, right? That would be kind of what we would hope to do here. And as we let k go to infinity, somehow assemble all those EKNs into a single set that, that has the desired properties. Well, everything up above showed that if you pick any epsilon and any delta, now I'm using delta here just for two reasons. For one thing, it's going to seem a little bit more like our familiar statement of uniform convergence, right? We don't usually talk about 1 over k. We talk about some very small delta when or you know, usually it's epsilon, but epsilon's already taken, so I'm calling it delta. In any case, but right, so we just talk about a very small, in this case, delta, such that the separation between the functions and delta is smaller than delta, right? So I'm trying to make it look a little bit more like the familiar idea of uniform convergence. I'm also free to do this because I know that no matter how small delta is taken, I can always choose a 1 over k, which is smaller, and put it sort of like in between there so that, you know, 1 over k is smaller than delta. And if I can, you know, right, so it's because I can do that, I can always guarantee that the separation is smaller than 1 over k and therefore smaller than delta, if 1 over k is chosen smaller than delta. Okay, so anyway, so that's why I'm kind of doing some of the moves here. So we have basically established that no matter what epsilon and delta you pick, there is always some set, I'm now calling it A. So there is this set A and there is an index n, such that A is very large, and for every index greater than n, and for all choices of x inside of A, the separation between the functions is smaller than delta. So if you have any doubt about how this follows from the earlier stuff, go back, watch it, right? Like just try to line it all up, try to prove it formally for yourself. But this does kind of summarize the important upshot of what we just showed. So we now have this as a principle that we can use in the actual ultimate proof of this theorem. So now let epsilon be any positive number and let n be the index guaranteed up here, so that, you know, if we choose this to be delta, right, like this is my delta that shows up, you know, up here, right? So I'm picking that for my delta. Let n again be the corresponding index, and let a sub n be the corresponding set, such that this inequality holds, and we effectively, you know, just kind of take everything that is given to us in what we just specified above. You know, specifying that the separation between the functions is smaller than 1 over n on a sub n. And now finally I can tell you what actually is that set A, right? The actual A from the main claim that we're trying to prove. A is the intersection over all of these a sub n's. That should hopefully make sense because you know, they are getting smaller and smaller. Or really, I guess it's not so much the smallness that should make intuitive sense, but the fact that that they continue, right, like with n growing large, the separation grows small, and so in a sense, like in the limit, the separation becomes as small as you want. And so at this point, I'm going to skip the demonstration that the convergence is uniform on A. I think that's fairly straightforward to confirm. Leave a comment if it's any trickier than I think it is. I'll make maybe a supplementary video, or possibly see what I could answer in like a comment or something. But in any case, let's at least focus in this video on the confirmation that it has the measure that we desire. And that is because there is this tricky thing, like, why did I say that delta is epsilon over 2 to the n plus 1? Well, you could have said epsilon and then see what happens. But you'll find that, okay, let's go through this. So, right, so let's talk about measuring e minus a, right, because we know we want that to be less than epsilon. That's the whole thing that we're trying to prove here. Now, how do we measure this? I think it makes good sense to try to use some kind of facts about measuring, unions, intersections, or something like that. I suppose one could have tried initially to measure this using excision. Actually, let's just toy with that briefly, just in case that maybe makes a more natural sequence of steps. So recalling that A is the, so here we would represent it like this, and then how could we, I guess at this point you would have to measure this intersection, and it's not clear how to do that. We don't have good, unless it's, sort of a monotone sequence and we use continuity of measure or something like that. It's not clear how we would use, or how we would measure that A. So maybe this is a bit of a dead end, and that's why I approached it in this other way, where I try to, turn it into a union, right? So if we're doing E minus A is this intersection, then we're doing E intersect the complement of A, and we can write the complement of A as actually the union of each individual complement, right? That's De Morgan's law. And this is a little bit more promising because, we know we have good theorems for measuring unions. So let's try to stick with this. Okay, so then what are we going to do? We're going to just do a little basic set theory that if you do E intersect the union, then you can move E intersection inside of the union. And then once you have E intersect AN complement, well, that's just the same thing as E minus AN. So we get this little move by basic set theory. And now that we're measuring a union, we had an earlier theorem, right? Like we can't necessarily use sigma additivity because we don't know that these sets are disjoint. But we can use the theorem, which says that even if you don't have disjointness, you still can get this inequality, and that's all we really need. So we use that theorem from earlier saying that it's less than or equal to the result if you take the sum. And then we'll use what we said, this measure mu E minus AN. We said that that is less than epsilon over 2 to the n plus 1. And right, I never fully explained why I chose epsilon over 2 to the n plus 1. Why not just make it epsilon? Well, you're taking this infinite sum, right? By the time you get to this point in the proof, if you had chosen epsilon, which was perhaps a reasonable thing to have done, but by the time you get here, you'd be taking an infinite sum of epsilon, and then everything just goes wrong because that turns into infinity. And we want this less than an arbitrarily chosen epsilon, right? We want this less than epsilon. So that's why we don't, right? Like that's why the decision up here was good to do epsilon over 2 to the n plus 1. In particular, because the epsilon can come out. Let me actually write out some more explanation of what's going on here. So if we move the epsilon to the outside of the sum, and I'm just going to be kind of lazy with my indices here because we all know what my indices actually are. So we could move the epsilon to the outside, and this is a geometric series, right? That's the reason for this particular choice, 1 over 2 to the n plus 1, is that this was chosen, right? Like, why wouldn't I have chosen epsilon over n if I don't want this thing sort of like blowing up to infinity, over here? Well, this would get you, right, if you move epsilon out of the sum, let's maybe go ahead and just write that. If you had this, well, that's the harmonic series, and that does not converge. So that's a bad choice too. So that, right, the reason for choosing specifically 1 over 2 to the n plus 1 here was that that's a geometric series, and we know that that converges. In fact, that converges to 1, so that this is effectively epsilon. And since that is, right, so that's what we get over here, and we have finally proved exactly what we set out to prove, that the measure of this difference is smaller than epsilon. And since uniform convergence happens on this set which is very large, then the proof is complete.